Well, again, so in this video, I want to explain an equation that you'll often see in textbooks that says delta G is equal to delta H minus T delta S. Now, earlier in another video, we showed how delta G can also be written using the delta notation as S delta T, there's a minus sign in front of that, plus V delta P, or in the video we showed it using the differential notation, so we had minus SDT plus VdP. And this is handy because we can define equilibrium as a state where there are no changes in Gibbs free energy, and that would occur when we have constant temperature or constant pressure. So it's kind of nice to have temperature and pressure as the independent variables. We could try to fix these, hold pressure constant and temperature constant, and when we do, then it's the Gibbs free energy that would be minimized and would go to zero. Well, how does this guy relate to this guy here, or more precisely, this guy to this guy? Well, let's take a look at the way we defined Gibbs free energy originally. Not us, but rather Josiah Willard Gibbs. He said G is equal to U plus PV minus TS. And in another video, we explained how that is related to, or actually is defined as H. So we can rewrite G as being defined as H minus TS. Let's use the differential form. So that means dG would be equal to dH minus TdS and minus SDT. So that's really the full form of the equation. What we can do is we can hold temperature constant. So at this point, let's let temperature equal a constant so it doesn't vary. So that means that dt is equal to 0, and that whole term drops out. Let's erase the chalkboard. We're just going to rewrite this. So that means we have dg is equal to dH minus TdS. Or if we want to write it using the delta notation, if we have finite differences, measurable differences in enthalpy, then we would have a delta H minus T delta S would give us the Gibbs free energy. So this is a way of talking about changes in Gibbs free energy. But notice that to get here, we had to do something special. We had to take the minus SDT term and have this thing drop out and go to 0. So this is a special case where we can only write this equation when we assume we have constant temperature. If we don't have constant temperature, then we would have to use the other expression. dG is equal to minus SDT plus VdP, or in delta notation, delta G is equal to minus S delta T plus V times delta P. So this would be the case where temperature and pressure are allowed to vary. So here T and P both vary, but in this case, temperature is equal to a constant. So this equation is fine, but understand that it is not the same as this guy here. They are a little bit different, actually very different, because we're holding a very important variable constant.